What if I told you that the difference between a chatbot that hallucinates and one that reasons like a senior engineer comes down to about 50 lines of prompt scaffolding? Chain of thought prompting was just the appetizer. The real reasoning power comes from three techniques that most developers have heard of, but few implement correctly: tree of thought, ReAct, and self consistency. Today, we're not just learning the theory, we're building each one from scratch, watching actual API calls, and I'll show you exactly when to reach for each tool. By the end, you'll have a reasoning toolkit that handles problems your current prompts simply cannot. Chain of thought prompting tells a model to think step by step. That's powerful, but it has a fatal flaw. It's a single path. If the model makes a wrong turn on step 3, every subsequent step builds on that mistake. There's no backtracking, no exploring alternatives, no way to say, wait, let me try a different approach. Human experts don't solve hard problems linearly. They explore, backtrack, and compare multiple strategies. The techniques we're covering today give LLMs that same capability. We're covering three distinct approaches. Tree of thought explores multiple reasoning paths simultaneously and selects the most promising one. Think chess grandmasters considering several moves ahead. ReAct interleaves reasoning with action, allowing the model to query external tools and ground its thinking in real data. Self-consistency generates multiple independent solutions and picks the most common answer through voting. Each solves a different failure mode of naive prompting. Imagine you're solving a puzzle where early choices constrain later options, like the classic 24 game where you combine 4 numbers to make 24. A linear approach might try one path and fail. Tree of thought systematically generates multiple possible first steps, evaluates which ones look promising, expands only the good branches, and repeats until finding a solution. The key insight: we're using the LLM itself to both generate possibilities and judge their quality. It's deliberate, structured exploration rather than hoping the first attempt works. Let's build tree of thought from scratch. We need 4 components: a thought generator that proposes next steps, an evaluator that scores how promising each thought is, a search algorithm that decides which branches to explore, and a solution checker. Here's the core class structure. Notice we're keeping track of the full reasoning path at each node. This lets us backtrack and also gives us interpretability into how the model reached its answer. The thought generator is where the magic happens. We need to prompt the model to produce multiple distinct candidate next steps, not just variations of the same idea. The key is being explicit about diversity. We ask for approaches that are genuinely different from each other. Watch how we structure this prompt. We provide the problem, the current path so far, and explicitly request to k different next steps. We also ask for brief rationale with each thought, which improves generation quality and gives us debugging insight. Now the evaluator. This is what enables pruning bad branches early. We ask the model to judge each candidate thought on a scale, considering both local quality and whether the overall path seems to be heading toward a solution. Notice we provide the full reasoning path, not just the latest step. This context is crucial. A step might look good in isolation, but terrible given what came before. We pass out a numeric score and use that to rank branches. For the search algorithm, we'll use beam search. It's the sweet spot between exploring everything and being too greedy. At each depth level, we keep only the top k scoring branches and expand those. This prevents exponential blowup while still maintaining diversity. Here's the core loop. Expand all current candidates, score the new thoughts, keep the best k, and repeat. We also check at each step whether we've found a valid solution. Let's see. Tree of Thought solved the classic 24 game. Combine 4 numbers with arithmetic operations to make 24. This is perfect for ToT because early operation choices heavily constrain later possibilities, and there's a clear solution check. Watch the terminal as we run it. The model generates multiple candidate first operations, evaluates each, prunes the bad ones, and explores deeper on promising branches. Notice how it backtracks from the dead end and finds the solution. Tree of Thought is your go-to for problems with high branching factor and verifiable intermediate states, puzzle solving, mathematical proofs, multi-step planning, code generation with tests. Anywhere you can score partial progress. ToT helps. But it's expensive. You're making multiple API calls per step, per branch. For simple questions, it's massive overkill. Reserve it for problems where getting the wrong answer is costly and exploration genuinely helps. Tree of Thought explores hypotheticals. But what if your problem requires real-world information? ReAct, reasoning plus acting, interleaves thinking with tool use. The model thinks about what to do, takes an action like searching the web or querying a database, observes the result, and then reasons about the next step. This grounds the model's reasoning in reality and prevents the confident hallucinations that plague pure reasoning approaches. The ReAct loop is deceptively simple. We maintain a scratch pad of all thoughts, actions, and observations. Each iteration, we prompt the model with this history and ask for either the next thought-action pair or a final answer. The key is the structured output format. We need to reliably parse whether the model is thinking, acting, or finishing. Here's the core loop structure. The prompt is everything in ReAct. We need to teach the model the thought, action, observation rhythm and the exact format for calling tools. Notice how explicit we are about the available actions and their input formats. Ambiguity here leads to parsing failures. We also show few short examples of the pattern. This is crucial for reliable structured output without fine-tuning. Tools are just Python functions with doc strings that describe what they do. The doc string matters. It's what the model reads to decide when to use each tool. Here, we define a simple search tool using a search API and a calculator using Python's eval. In production, you'd add safety guards around eval. The executor just looks up the function by name and calls it with the parsed input. Let's see ReAct handle a question that requires real-world lookup. We're asking about a recent event that the model's training data doesn't cover. Watch the scratchpad. The model thinks about what information it needs, calls the search tool, observes the result, and reasons toward the answer. Without ReAct, this would be a confident hallucination. With ReAct, it's a grounded, verifiable answer. ReAct isn't bulletproof. Common failures: the model loops asking the same question repeatedly, it calls a tool with malformed input, or it finishes prematurely without actually using the observations. Fixes include adding iteration limits, implementing retry logic with clarified inputs, and explicitly prompting the model to incorporate observations before finishing. You can also add a simple check. If the answer doesn't reference any observation, force another iteration. Now for self-consistency. The simplest but often most effective technique. The idea: sample multiple independent chain of thought responses at high temperature, then take a majority vote on the final answer. Different reasoning paths might make different errors, but the correct answer tends to appear more often than any particular wrong answer. It's ensemble learning for language models, and it works shockingly well for math and reasoning tasks. Implementation is straightforward. Call the model n times with temperature above 0, pass out the final answer from each response, and return the most common answer. The trick is in the answer extraction. different reasoning paths, phrase answers differently. We use a normalization step to match semantically equivalent answers. Here's the core implementation with basic normalization. The tricky part is making voting work across varied phrasings. 42, 42, the answer is 42, and 42 should all count as the same answer. We use a multi-step normalization. Extract from the answer tag, lowercase, strip articles, and filler words, normalize number formats, and remove punctuation. For more complex cases, you can use embedding similarity to cluster semantically equivalent answers. Here's self-consistency on a math word problem. Watch how different samples take different approaches. Some make arithmetic errors, one completely misreads the problem. But the correct answer emerges from voting. The confidence score tells you how much the model agreed with itself. Low confidence? Maybe run more samples or use a different technique. This is actionable signal for production systems. Here's where it gets powerful. Combine these techniques. Use tree of thought to generate candidate solution strategies. Run each strategy through ReAct for grounded execution. Then use self-consistency across the ToT branches to pick the final answer. Or simpler, use ReAct as a tool within ToT. One of your thought branches might be, look this up to verify. The frameworks are composable building blocks. Match the technique to the failure mode you're trying to address. Quick decision framework. Is the problem factual and requires current information? ReAct with search tools? Is it a complex reasoning puzzle with verifiable steps? Tree of thought. Is it a calculation or logic problem where the model might make random errors? Self-consistency? Not sure? Start with self-consistency. It's cheap to add and gives you confidence scores. Then add ReAct if you're seeing hallucinated facts. Save ToT for genuinely hard problems where exploration helps. And remember, these techniques cost more tokens and latency. Use them deliberately, not by default. You've just added 3 powerful techniques to your prompting arsenal. Tree of thought lets LLMs explore multiple reasoning paths systematically. Use it for puzzles, proofs, and planning. ReAct grounds reasoning in reality through tool use, essential when you need current or external data. Self-consistency uses ensemble voting to smooth out random errors. Dead simple to add and surprisingly effective. Next up in the AI track, we're building a full autonomous agent using LangGraph that combines all 3 techniques. If this leveled up your prompting game, smash subscribe and drop a comment with your most challenging prompting problem. I genuinely want to hear what you're building.